Okay, now I started. Okay. So we're on SL. Do you want to do some paper 1 first?
Sure.
So the paper 1 is multiple choice, I think, right? I don't think she'll give us. Do you think she'll give us multiple choice?
I doubt it, but
Yeah.
probably more for your response.
Yeah. Well, we can take a look at it. And there's no paper 3 for us, right? For our year, I don't think there's paper 3. Okay. So the SL paper 1 mark scheme, does it have the answers on them too? Because oh yeah, it has the answers. Okay. So for this one, says the energy level diagram for an atom has 4 energy states shown. What is the number of different wavelengths in the emission spectrum? Would that just be 6?
Yeah, I think it's 6.
That's like you just draw the number of falls, right? So 1, 2, 3, 4, 5, 6. Yeah. We can use this. I think we just need to be careful not to over scroll.
Yeah.
Let me zoom in further. That way we don't make it. Okay. So the graph of the variation of average binding energy per nucleon with nucleon number has a maximum. What is indicated by the region around the maximum?
Is it C?
I would think so, because anything that has the most, right, doesn't make sense where fission is most likely, fusion most likely. Fusion is more likely to occur for smaller, right?
It's just, you can't say like the region around the maximum because like,
yeah,
I mean, it could be either one, and also you're right, it would be like further
yeah,
down.
it would be further down because hydrogen, I just know that hydrogen really likes fusion.
Yeah.
It is C. Okay.
Okay.
Detector placed close to a radioactive source detects an activity of 260. Is it becquerels? How do you pronounce that?
That's what I thought it was.
Okay. The average background activity is 20, and the nuclide has a half-life of 9 hours. So what activity is detected after 36 hours? That's 4 half-lives, right?
Yeah. Is it B?
How do you know? Wait, how did you find that out?
I just did 260 over 16.
260 over, because it's 4 half-lives, so 2 to the 4 is 16. 260 over 16 is, wait, what's 260 over 16?
16.25.
Oh, it's 16.25. So B then? It's a D.
Oh.
I think you have to take this into account. I haven't seen problems like this. I don't have
average. I don't know what that means.
That's like the background. So maybe you have to just subtract that from the normal one first. So like, do you do 260 minus 20 first? So like, it says it detects an activity.
Oh, I see. Okay, yeah, that makes more
240.
sense. I see.
If you have 240 to begin with, then you divide that by 16, you get.
Okay, yeah, I didn't understand what the average background activity was, but yeah, that's what it is. Because then if you divide 240 by 16, you get 15, and then you have to add back in the 20 background. So 15 plus 20.
Oh, okay. Wow, that's a complicated process. I was like, I'm getting 15. Why is it 35? Okay, so you add that back in because it's detected, right? The detecting, they can't. Okay. Wow, that's tricky. It's not hard. It's just like you have to take that.
It's just like, yeah.
Yeah. Okay. Average binding energy per nucleon of 15.8 oxygen nucleus is 7.5. Total energy required to 7.8.
Is it C?
Just do that times 15. Is that it?
Yeah, but that seems really simple, like the last one. But
sometimes it is really that's okay. So 7.5 times 15.
I mean, it probably is for this one.
Yeah, 113.
Yeah,
it is C. You have to be careful. Yeah. They give you plenty of time too on the exam, I think. So
Oh, really? Okay.
yeah.
Yeah, I think that's what Miss Raja
Well, yeah, what Miss Raja said was math is super fast, but physics is like,
Yeah.
yeah. So the half-life of a radioactive sample is 5 days, element is 5 days. There's 128 grams. After how many days will there be 16 grams? So 128 over 16 is 8, right? So that is 3 half-lives because 2 to the third power is 8.
Sorry.
It's okay,
yeah,
it's okay. I know I went, so 128 times 1/2 to the what power 16 is essentially what we're trying to find, right?
Yeah, 1/8. So 2 to the power of 3. So 15, yeah.
So yeah, three half-lives, and if it's 5 days, the 15 days. Yep. See. Okay. Atomic spectra are caused when a certain particle makes transition between energy levels. That's an electron, right?
Yeah.
And that's just definition. Sample contains an amount of, how many of these do you want to do? Because I feel like they have a lot. Do you want to do like 20 minutes of this and then 20 minutes of the other one? Or what?
Maybe we should do a little bit more for response, since that's
response?
like,
Yeah.
Since that's like more likely to be on the test.
Okay. Yeah, I mean, maybe we can just switch over in 5-10 minutes because these seem to go pretty fast.
Yeah.
Sample contains an amount of radioactive, okay, half-life 3.5 days, so 2 weeks. So 2 weeks is 4 half-lives, right? So 1 half-life gives us 50%, then 25.
So C.
Then 12, then 6. Yeah, 12.5, around 6, I would say, right? So C, yeah. Oh, and we don't have I don't think you get a calculator in paper 1. So we need to get used to doing the, yeah, I don't think so. I'm not sure. So we just have to get comfortable doing these. I think we could have done them like.
I mean, we could have. It's just kind of annoying.
Yeah, they're not hard. Just we're not used to. Nuclear fission reaction, X splits into Y and Z. Which of the following gives a possible order of the nuclei from lowest to highest binding energy?
Lowest to highest, so
X should have the lowest, right? Because it's most unstable.
Yeah. So probably D.
D probably, yeah. Yeah. I think they tried to trick people by putting Z first. I don't know why. Okay. Bismuth 210 decays like that. What are the mass numbers and proton number of Y? That's an interesting notation. So it's like I think we have to work this out.
Interesting.
Yeah, it's like that's a beta decay, beta minus decay, and alpha decay. So like it's easier probably to write it out. So bismuth has 21083, right? And that goes into X, and then a beta minus.
I mean, yeah, you just continue. But
yeah, you're probably right. I can't go that fast. That's 1 minus, and beta has 0 mass, right? Beta minus has 0 mass. Yeah, so then that should also be 210, and this will be 84, I believe.
Yeah.
Okay, then that'll go to Y with alpha decay, which is 24. And then if alpha is, we still need a total of 83. Oh, so essentially you don't even need to do this mid step, right?
No, you do. 84. It changed to 80. I mean, if you could see that it changed from 83 to 84, the proton count, then you wouldn't need to do the middle step. But if like you needed to see the beta decay.
Oh, because it's just the X that's turning into Y. It's not the bis. I see. So like once the beta particle is gone, it's gone. I see. Okay. So 82, and that's 210, right? So 210 minus 4 is 206 then?
Yeah.
And then that means we need 82 protons and then mass number 206.
Yeah.
B then. Okay. Let's see. Oh. Yep, it's B. Initial number of atoms is n. The radioactive half-life is defined as time taken for, is it C? It's not B or D. It's definitely, half-life isn't probability. It's either A or C.
Yeah, it's C.
I think it's C. Yeah. Which of the following is true about beta minus decay?
C?
Yeah, anti-neutrino. That's just factual. I don't think there's a working. Geiger Marston. So this is the Rutherford bullet foil experiment. Small fraction of the alpha particles were deflected through angles greater than 90. What does this observation suggest about the nucleus?
D.
Yep, D. Yeah, that one. I feel like we're not going to get questions like this.
Yeah, definitely.
The nuclear decay reaction here would be best described as, this one's easy, just alpha decay, right? Or no?
Yeah.
I have to be careful.
Well,
Could be fission or fusion. I mean, is this fusion or alpha decay? Nothing's decaying.
It's not really decaying. Yeah, I think it's.
Yeah, it's fusion. Yeah, we have to be careful.
But then, not that what is neutron capture again?
I don't. Neutron capture is just, I think, when you shoot a neutron and then it gets captured. I believe. I don't know. We can search it up. Neutron. Atomic nucleus. So yeah, so it's like when you form a heavier nucleus. It's like fusion, except it's, I don't know if it's fusion. I don't
Isn't
know
that like bombardment or whatever?
Yeah, bombardment. Yeah.
Okay.
So, but yeah, this is fusion.
Probably fusion. Yeah.
Yeah, because, and in order for it to be alpha decay, you need to go from a heavier nucleus to a smaller nucleus, right? Okay. The definition of unified atomic mass unit. Oh, this is just another definition. B. Yeah. We learned that in chemistry, and isn't that the same for like the mole, like what a mole is? 1 mole, like 1/12 the amount of, I don't know, something like that. It's defined in a similar way. Yeah. Which of the following affects the rate at which a sample? This was on the homework, right? Or somewhere. It was somewhere on the. It was on the. Yeah.
It's just the mass, right?
Just.
I mean, it's not temperature.
Yeah, I believe it's, yeah. So I think radioactive, like we often think, temperature and pressure change and volume can change like the speed of a reaction, but in radioactive decay, it just depends on how much is present, right? So in this case,
it's like, I think it's good to remember that it's like random. I think
random. Yeah. Okay, nucleus P decays by a sequence of emissions to form Q. Alpha particle, 2 beta particles are emitted in the sequence. Which statement is correct? Do we need to write this out? Maybe it would be helpful. Yeah, it would be helpful. Yeah. So P, it has some Z, it has some N, right? I think that's an A. Either way, whatever it is. That becomes a Q, and then we have an alpha 2, 4, and then we have. I'm gonna write the beta twice. Actually, no, we can write it like this: 1 minus 0. Okay, that means we have a 2 here and a 2 minus here. So it means it has the same number of protons, right? Or Z, not 2, Z. That's why I should. Okay, Z. And then mass, we have 4 here and 0 here. So this is just A minus 4.
Yeah.
So nucleus P has.
It would be B, right?
An isotope, yeah, I think it would be B because they have the same number of protons, different number. Let's see, it is B. Good. You want to switch over now, or do you want to do a few more of these? I think we're pretty good on this, if I'm being honest. Like, this doesn't seem too bad, except for when there's a weird question that just throws us a complete curve.
Yeah, we can switch.
Okay. Oh, I'm going to keep that open. I'm probably going to do some more later. Then paper 2. This is with the Marx team or without?
So like, can anyone access this, or do you have to
Yeah,
download whatever
anyone
it
can.
is?
You know what? Let me send a link here. Let me send a link to the Slack. That way, because it's difficult to once you access it, it's fine. It's just difficult to get there.
Okay.
Low system resources. That's the paper 1, and then this is paper 2. Do you just want to start from the top?
Sure.
Nucleus of iodine isotope I-131 undergoes radioactive decay to form. We should probably write this down. Iodine 131 forms xenon 131, and it's stable. So that means we had to have some sort of beta, right? 0 beta. I don't know if it's beta minus or plus yet, because I don't remember where it's. So initial activity of I-131 is 100 kilobecquerels. Okay, interesting.
So we don't get the periodic table?
No, we don't. But most of the time you don't need it.
Okay.
Like you sometimes, it's like they give you just enough information to be able to figure it out. Okay, so clearly exponential decay. This one is a very common question. They love throwing this. Explain what is a nuclide and what is an but those are easy, so that's good.
So one thing, are you supposed to say like atoms or nuclides?
Nuclides. So isotopes are nuclides with the same number of protons but different number of neutrons. Yeah.
Okay.
That's why it's like here they said it's different. Yeah, they said it differently. But nuclides is the sure, like you're not gonna get it wrong if you say nuclide. Because that's what they are. That's what they are. Like nuclides, that terminology is introduced so we can describe what isotopes are, isotones, and things like that. Okay. Okay, so like here they tell you it's 53. Like they give you just enough.
Oh, okay. Yeah.
So
And
that's
beta minus.
Yeah, exactly. That's 1 minus. That should be 0. And here we have to have an antineutrino, right?
Yeah, and 54.
54. Yep. So that the charges are conserved.
Didn't we do this?
Did we do it?
I don't know.
I don't think so. This one, I don't remember this medical application.
Yeah. Okay.
54 and antineutrino. Good. Okay. The I-131 can be used for medical application, but only when its activity lies between 20 plus minus 10 kilobecquerel. So between here, is that right? Basically in that range.
Well, no, that's the days actually.
Oh, whoops. Good catch. 20, and then that's 10, and then that's also 10. So determine an estimate for the time during which it can be used. So that is around where? Right there?
Like 17 to 18.
Yeah.
Or sorry, not 17. Like
14,
14.
Oh, 11, 12, 13.
Like 13 to 14 is what I meant.
Yeah, so 13 to 14. So I think you should just pick one probably, and I'll probably 14. Just go with 14. Yeah, I would go with 14. And then this one looks like it's
that one looks like
25.
26 to me, but
26.
I don't know. I don't think it really matters.
Oh yeah, I think they'll have like a range. So okay, we can say 14 to 25, 14 to 26 days. We should specify the unit. Well, range is 14 to 26 or 14 to 27. Wow, interesting. So like they were strict about the 14, but now they're about, like they were either 26 or 27. So I guess on the paper, I think that's what you should bring a ruler with you on the exam.
Yeah.
Yeah, because like they're gonna be.
I think it's also because like your line was kind of covered.
Yeah, I know.
Yeah.
Yeah. We all know how good my lines are on. Okay. Different isotope has half the initial activity and double the half-life. On the graph, see sketching the variation of activity with time. So half the initial activity. So initially we start at 50.
Start at 50, and then it'll take twice as much time to.
The half-life of this is what?
Looks like
Looks like 5, 6,
8.
8. Yeah, I think it's 8 too.
So this should be 16 days.
Double, did it say double the half-life?
Yeah.
Okay. So 50, then 25 should be at
That's
16.
30.
Oh, whoops, 25 should be at 16 then, right? That's 15, that's 16. So it should be 22, 24, 25, like right here.
Yeah.
Okay. And then half of that is 12.5. 10, 12.5 is like going to be right here somewhere, and it'll be 32, I believe. 31, 32, 12.5, right there probably. And then do we need to do one more? What's half of 12.5? Oh, we can use our calculator.
Yeah. 48. Yeah, you can fit one more. Just be right again. 48.
48. Okay, so 48 is, oh my God, right there. That's 48,
Yeah.
and we're going to be at 6.25. So that's
like about 6, basically.
2, 4, yeah, 6. Is that 6 right there? No, 2, 4, 6. This line. Yeah, the straight edge is going to be super helpful.
They made it weird, like the scale, because the bottom it's on a scale of 50.
Bottom, yeah. Okay, so and then we just yes, you get the point.
Yeah.
For now. Okay, what's half-life is 16 days, line passes through 16, 25 within a small square. So they want it through 16, 25. We did that, yeah. Starts at 50 and approximately exponential. Okay, so like this one, they just needed you to do the first point, but sometimes they require you to do more, so it's better just to do as many as you can on there. Okay. Have we done this one? We did, right? This one was the one we had on our quiz. Yeah, with the why they put nickel. I have no idea. Also, so when you're doing the graph, it needs to look like this or whatever, and then it needs to look like this, right? It can't go down all the way, because then it would be.
Yeah. Is it like completely? I don't know if it's completely straight.
I don't know. It's the weird, like the wording that they have here. It says line must not flatten out towards second mark. What does that mean? Does that mean flatten out as in like this, flatten out like that, or does it mean flatten out and like flatten out and have start?
That's
what does
how
it mean?
I did. I thought they meant that like it just can't go like straight like that. No.
Oh, it just can't go. So you did what? You did this?
I did like something similar, maybe a little bit steeper,
Yeah,
but like similar to that.
I think that's right. Okay. All right. Yeah. Did we do this one yet?
No. Oh wow.
Wow.
Waves.
Waves, yes. So this is nuclear model of the atom. So the nuclide
question.
Yeah, it is. Oh wait, this is what? Why is part 2 inside it? Oh, I think it's because they like took the whole thing. So we just need to do part 1. So part 1 is about the nuclear model of the atom and radioactive decay. Nuclide radium-226 decays into radon. Let's write this out. They'll probably have a student question. But I just find it easier to always write it out and see what's going on. Radon, then there's an emission of alpha particle 2,4, and gamma ray photon, right? Nothing else? I believe that's it. And then that should be 86, and that should be 222.
Yeah.
Okay. So outline how the evidence applied by the Geiger Marston experiment supports the nuclear model of the atom. So there's 4 marks here. What are the 4 points? So first, you would probably say what you expect to happen, right?
Yeah.
You expect for them to go straight through with little deflection, right? Okay. So expect straight through, little deflection. then what happened was,
Many were deflected and some actually bounced back, right?
alpha particles, yeah. Alpha particles, most alpha particles shot at Ghosh foil. Oh yeah, we have to state that. Our alpha particles shot at thin AU foil. Most went straight through, but some were deflected back strongly. Suggests that nucleus, that atoms have small positively charged nucleus with most of the mass, right?
Yeah.
Or how do you say that? Dense positively charged?
I said, oh wow, the echo is strong. Tiny, massive, positively charged nucleus.
Tiny, yes. Tiny, massive, positively charged. Okay. Let's see what they want. Blah, 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 blah. Okay. Most undeflected, pass straight through. Good, we had that. Oh, we should have stated the mostly empty space part. Okay.
Bounce back, yay.
You deflected, yes. Bounce back. Okay. Hence, small dense nucleus. Good. So we got 3 out of the 4. It's very
What's the other part?
The mostly empty space part.
Is there something under below?
Oh no, that's the second part of the question.
Oh, okay.
So these are frustrating because like when you know it and it's just like you don't think to write it down.
Yeah.
Um.
Because you could just like write everything you know and that would
Yeah, like that would take forever. Exactly. Okay. I think for the most part though we understand it.
Mm-hmm.
Outlined by classical physics does not permit a model of an electron orbiting the nucleus. Oh, because this is Maxwell, right?
Yes.
Because in classical mechanics, in Maxwell's, okay, so electrons, the first thing would be electrons orbiting the nucleus are accelerating, right?
Yeah. And if they're accelerating, they have electromagnetic force or radiation? Is it force or radiation?
Accelerating charges generate or produce electromagnetic waves.
Oh, okay, waves. Okay.
Yeah, waves. However, electrons orbiting nucleus don't. Nucleus don't. I think that I don't know what else to put. Hence, and I think you would need the conclusion as well. Hence, classical physics does not permit orbiting of electrons around nucleus. Let's see. Electron accelerated. Oh, or a mention of centripetal force. Yeah. So acceleration, yeah, because of the center. Yeah, either way is fine.
Oh yeah, and
should radiate electromagnetic waves or energy. Oh, inspire. Okay, because they're losing energy over time, right?
Yeah.
Okay. So that's the. See, once again, it's like, yeah, we knew that. It's just how much do we put on there? That's. I think what I would do is probably go back to those questions at the end and double check. And like if I have more time.
I feel like if I had more time, I would just like add
dump everything I can. Yeah. Okay, this is the same question. Nuclide is a particular nuclear species with a certain number of protons and a certain number of neutrons.
I think they like for people to say like characterized by.
Oh, characterized by.
Yeah.
Yeah, nucleus characterized by a specific number of neutrons, protons, and neutrons. Okay, an isotope we already said. Okay, so this is alpha decay.
What was the word again? Like species or something?
Yeah, nuclear species or atomic species.
Okay.
2, 4, and gamma. We don't put anything for gamma, right?
Yeah, I guess you just put 0, 0.
Can you just leave them blank? But it's 3 marks. So they're probably looking for 2, 4, and then 86, 224. That's it. Because I mean, I guess you could put 0, 0, but
Yeah. I
let's
mean, it
see.
wouldn't hurt. Also, it's 222.
Oh,
You
what did
you put 224.
oh yeah, 222. Yeah.
Did they put 0, 0?
Yeah, helium or zeros. What? Okay, so you
Oh.
get 1 point for 222.86,
Oh.
and then you get 1 point for doing either 24 or is it? That's very weird. I don't know why they would do that, but okay. So I
That's
guess the
interesting.
moral of the story is you should put it down either way.
But it says that top and bottom numbers balance correctly, so you can't get full points unless you do the
Yeah,
helium anyway.
yeah. Oh, yes. That's weird. Okay, so essentially even if you didn't put the gamma, you could have still gotten full credit.
Yeah.
But I guess just to be safe, you should fill in the blanks wherever you can. Okay. Now, radium-226 has half-life of 1600 years. Wow. So we want to find 1/64. So 1 over 64 is equal to 1/2 to what power? 2, 4, 8, 16, 32, 6.
Yes.
So that's the 6th power. That means that's 6 half-lives. So 6 half-lives is 6 times 1600, which is 9600.
Yeah.
9600 years. Yep. Yeah. So so in this case you get 2 points. Not you could have directly went here. I would prefer to show the word just in case, but you get 2. In this case, you get 2 marks just for the right answer. It's a very weird phrase. Bald correct answer.
Yeah. I fully forgot everything about waves.
Yeah, I feel like I forgot everything about waves too. And I think we even did this problem, right? I don't know. We might have.
Yeah, probably.
Okay. Yeah. Did we do this one yet? We don't need to do
No.
collisions. We just need to do this first. So this is the
actually, maybe.
I don't
Probably
think
not,
we've done
actually.
this one.
Yeah.
Possible fission reaction is that. Okay, uranium breaking down into that. So first part is state the value of X. Basically just needs to balance, right? So you need to use mass in order for it to balance. So 92 plus 141 is 233. So the krypton and barium, is that barium? I think so. Make 233 in mass, and we have 235 here. So that means we had to have 2 neutrons, right?
Well, there's another.
Oh, there's another neutron here. So that's 3 neutrons then. Oh, that's right, because then there's 2 neutrons there. 236, so 233 plus 3. So that means X is equal to 3, which is pretty sure that's right. Yep, X. Show that the energy released when one uranium nucleus undergoes fission is that much. This is just like that problem we did in the quiz as well, right? It's similar to that.
Yeah. So should we just like say the steps, or do you want to actually like work it?
You can actually work it real quick, and how about you narrate the steps and I'll work it out. That way we can do.
Yeah, sure. So to
do
save time.
It's
You can
uranium.
just say that.
Yeah. Okay. Go ahead.
You can say that there's 2 neutrons
on the right
instead
side
of like 3 and 1. You know.
Yeah.
And then you just do.
I would do uranium on the left. Uranium minus. I would do everything on the left side minus everything on the right side, right? Because that way I get positive. Because it's energy released, right?
Yeah.
234.99333 minus 91.90645 minus 140.88354 minus 2 times 1.00867. So that's in unified mass unit. And then we have to multiply that by 931.5, right? To get mega electron volts. And then once we get mega electron volts, we have to convert it to joules. Oh my God.
What does the data booklet give? Like what?
It gives you the data booklet doesn't, so it gives you the charge of the electron. So you just need to know that one electron is, it gives you the charge of the electron as 1.6 times whatever many coulombs.
Yeah, but does it give you like I don't know, MeV to joules or something like that?
No, it doesn't give that. So you just need to
Does it
know
give-
that
does it
one
give you
electron
to-
volt. Yeah. So you just need to remember that one
Oh,
electron volt is this many joules. Or yeah.
oh, you need to remember?
No. You just need to remember that one electron volt is whatever, right? Because a volt is a joule per coulomb. So the coulombs will cancel. So all they give you in the data booklet is these numbers here. And you need to figure out the conversion on your own. You understand what I'm saying? So like they tell you that this is the charge on the electron. It's 1.6 times 10 to the negative 19. So you just need to, using that fact, you need to know that whatever mega electron volts I have, if I multiply that by, for every electron volt, I have 1.6 times 10 to the negative 19 joules, and electron volts cancel. And then you also have to divide by 10 to the 6 in order to get rid of the mega, right?
Okay, yeah.
Times
Or you can just
1.6.
do 10 to the negative 13th in your calculations.
Yes.
If you know you have mega electron volts.
Yes. And that gives us 2.7 times 10 to the negative 11.
Yeah.
Let's see if that's, I think that was what they wanted, right? 2.8 times 10 to the negative 11. Oh, there, yeah, if you round properly, it's 2.8. Good. So our methodology was correct. So it's just unit subtraction, addition, and then unit conversion. State how the energy of the neutrons in A is likely to compare with the energy of the neutron that initiated the reaction. Should be greater, right?
Yeah.
Because there's release of energy, so there should be more, should be faster, higher kinetic energy, or more energy, whatever it is.
Yeah, more kinetic energy. Is that what you're supposed to say?
I would think more kinetic energy, but I would just say more energy because energy is released. I don't know how else to state that. Let's see. Yeah. Okay. Greater, higher energy. So yeah. Oh, you just have to state that. There's no, like, you don't need to say that.
That seems weird. Isn't that what the question? Oh, okay, never mind. But I feel like that's kind of obvious because it's releasing energy. But
yeah. What is this? Part 1 uses neutrons. I don't know what that is. That. Oh, I think that's for the next part. Oh wait, this one. The nuclear power plant. Okay, we haven't done energy stuff yet, so I don't think we can do that. Outline the role of the moderator. That's for this thing here, right? Or no? What's the moderator? Oh, the moderator? Is that talking about like the moderator in a nuclear power plant? That's the energy unit that we haven't done yet, so I don't think we need to worry.
Moderator, like the thing that stops it from creating a chain reaction.
I think so. I'm not sure exactly. Okay. Okay. That's auspicious last nuclear fission. We did this one. No, we haven't. Right. This one's new.
Yeah, I think it's new.
Reaction that places in the core of a nuclear reactor. Okay. They tell you that this many fissions take place every second. Each fission has this much energy, built for conversion to electrical energy. The overall efficiency is that much. In addition to U-235, the nuclear reactor contains a moderator. Oh yeah, so this is the moderator that I would have explained the function of them. Obviously we don't know that yet, so we don't need to worry about that. Determine, oh, this is for the first part, I think.
I don't think we can answer these.
We can't answer these. We could do this one, determine the mass of, but even then, this is all part of the next unit, so we don't need to worry about that now. No point in figuring this out now. Okay. We did this. This was on the quiz, right?
Yeah.
Why is this even? Oh, Rutherford model. Isotope is stable, but this stable. Okay. So this isotope is stable, but this isotope is not. It says the alpha particles used to bombard a thin gold foil pass through the foil without. Is this how it's going to be on the exam, where they give you two parts all at once that have nothing to do with each other? Because that's kind of annoying.
Yeah, I don't know.
Okay. Few alpha particles are deviated from their original direction. Use these observations to describe the Rutherford atomic model.
We did this, right?
Yeah, we don't have to go over it again. Why?
But basically, what you need to have is like it was most passed straight through, because that means that there's a lot of empty space.
Yep.
And then a few were deflected, which means a tiny,
small, massive, positive,
tiny, massive nucleus.
Positively charged.
Yeah.
What do they say here? But there's 5 marks. Why do they have 5 marks? Nucleus is positively charged. Most alpha is not close enough to be deflected. Oh, atom is empty space. Oh, I think we're not getting the whole question here. It's like messed up here. So,
Okay.
Yeah, I think they want you to probably draw a model or something. Anyways, outline in terms of the force acting between nucleons. Why for large stable nuclei such as AU-197, the number of neutrons exceeds the number of protons.
To count so that wait, let me try to explain this. So it's because strong nuclear force is close range, so you need more neutrons to have enough strong nuclear force to
overcome
the repelling of protons.
Coulombic repulsion.
Yeah.
And then that helps you by adding more neutrons, you get to higher binding energy per nucleon, which helps you get more stability. I think that's 4 points.
Well, not really. I mean, does it?
I mean, for larger nuclei, most of the time. It's not a general rule.
I thought for larger nuclei, when you add more nucleons, it decreases stability.
Yeah, that decreases stability. Yeah, I think you would just talk about this then. Talk about Coulombic repulsion, mention a strong nuclear force, then balance. Yeah, okay. And then for this one, emission of electron and another particle. Okay, if there's a beta particle, that's beta minus particle, then also you're gonna have an antineutrino. Pretty easy. Okay. Okay, let's see. Nuclide of deuterium and nuclide of tritium undergo nuclear fission. Each fusion, it releases this much energy. Calculate the rate at which tritium must be fused to produce a power. Oh, that's the energy. Do you want to try this one, or do you want to just skip it for now? Yeah, skip it. Yeah, we don't need to do that. We can do this one though. It has a half-life of 4,500 days, decays to helium. Determine the time at which 12.5% remains undecayed. So that's how many half-lives? So 1 half-life would be 50, 2 is 25, 3 would be 12.5, so 3 half-lives. So 3 times 4,500 is 13,500.
Yeah.
Okay. You can do this in your calc. So yeah, 13,500. We haven't done Feynman. That's 7.3. We haven't done that yet. This is also 7.3. Yeah, we haven't done that. I think we're at a point where we've answered pretty much all the questions we can from what we know. You want to try this one?
Yeah, I mean, I think it looks pretty similar to what we've done.
Yeah, I think we can wrap up because honestly, yeah, there's no.
Do you want to do a few more?
Yeah, a few
multiple
more and then
choice?
multiple choice.
I mean, it seems like
Yeah.
most of those relate to.
Yeah, these are now going into the. There's a few more here but there's no. Yeah, we can do these on our own.
Yeah.
Let's
Or
do
we can
four
wrap
more.
up. That's fine too.
Let's do maybe like 5 or 10 more multiple choice depending on. Let's end at like 5 more minutes and then.
Okay.
We'll do the following. Oh, sorry. Whatever. Do the following correctly identifies the 3 particles emitted from here to here. So we're gaining charge, right? So that means we have to lose charge.
Well, it can't be an alpha, so you automatically know that it's not A, C, or D.
Yeah. Yeah. So it's beta minus and then antineutrino and yeah, B. That's the only part. Yeah. Mass of a proton is this much. The energy of proton at rest is therefore how much? So it's just that times c squared, right?
Mm-hmm.
So it's just 938 mega electron volts. Is that it?
Yeah.
So 938 times 10 to the 6 electron volts, the same as 9.38 times 10 to the 8 electron volts, right?
Yeah.
Oh, wait. You multiply that mass. Oh, yeah, you multiply by c squared, which is what we did. So now,
Yeah.
is the answer just C then?
Yeah.
Oh, sometimes these are, I don't know, I just get psyched out by these because they're so easy sometimes. Okay. Simple model of hydrogen atom suggests that the electron orbits a proton. What's the force that keeps the electron in orbit?
Centripetal is what they said before, right?
See, but the centripetal force isn't a force. I don't know. I mean, at least the way I learned it in AP, they were like, whenever it said basically like whenever it asks you what is the force, you should never say
Then
that it's a
maybe-
centripetal, because the centripetal force is all the forces acting in the centripetal direction. That's all it is.
Then it's probably gravitational, right? Because
Wouldn't it be electrostatic?
I have no idea actually.
Electrostatic, because that's the electrostatic. The electrostatic
it's saying
attraction is what's
what's keeping it in orbit. Then yeah.
Oh, A? Yeah,
Yeah.
A. Yeah, I don't think centripetal is ever like if it asks what type of force is it, like it can only be electrostatic, gravitational, strong, or weak. I don't think it could be.
Okay. Yeah.
Centripetal is just the consequence of whatever force is acting.
Yeah.
Yeah, there you go. It tells you what is the nature direction. To distinguish, it's best to use the word adverb it centripetally.
Okay.
Yeah, many different forces, all of which exactly. Okay. The Geiger-Marston experiment provides evidence for, we already talked about this, dense positively charged.
Yeah.
The emission and absorption spectra provide evidence for
D.
atomic energy levels, D. Data concerning nuclides are plotted in the axes below. What are the axes labels? This is the
A.
binding energy per nucleon and the number of nucleons, I believe. So A, yeah. Yep. What is the relationship between, oh, okay, that's easy. I'm not even, okay, all right, I think we're good. We're good. All right. That's pretty much it. Anything else we need to mention before we end for today?
No.
Okay.